Hello! In this video, we are going to prove the following theorem. Let xn be a sequence of real numbers if the infinite series from n equals 1 to infinity of xn converges, then the sequence of xn's converges to 0. And the contrapositive of this is telling us if the sequence of xn's does not converge to 0, then the infinite series does not converge. So this is sometimes called the nth term test. And so to prove it, let's suppose that the infinite series converges. And from here, the whole goal is to show that the sequence of xn's converges to 0. Now, since the infinite series converges, this is another way of saying that the sequence of partial sums converges. So we're saying it means that this sequence converges. But every convergent sequence of real numbers is a Cauchy sequence. So that means that this sequence is a Cauchy sequence. And by definition of a Cauchy sequence, to say that this sequence is Cauchy means the following. It means for every epsilon greater than 0, there exists a positive integer h, such that for every p and q greater than or equal to h, the absolute value of the pth term of this sequence minus the qth term of this sequence is less than epsilon. Now remember, our whole goal is to prove that the sequence of xn's converges to 0. And by definition of the limit of a sequence, to say that the sequence of xn's converges to 0 means the following. It means for every epsilon greater than 0, there exists a positive integer k, such that for every n greater than or equal to k, the absolute value of xn minus 0 is less than epsilon. Now, for notational purposes, we're going to change the variable n here to something else. We're going to change it to j. Right? It doesn't matter if we do that. It still means the same thing. So now, the whole goal is to show that the limit of the sequence of xn's converges to 0. And so to do that, we're going to prove that this statement is true. And since we're trying to prove a statement about every epsilon greater than 0, let's give ourselves an arbitrary epsilon greater than 0. From here, we want to show that there exists a positive integer k, such that this is true. Okay, now since we know that this sequence of partial sums is Cauchy, that means we know that this statement right here is true. And this statement works for every positive real number. So in particular, it must work for the positive real number epsilon that we just introduced. So, taking this positive number to be epsilon, we have that there exists a positive integer h, such that for every p and q greater than or equal to h, the absolute value of the pth term of the sum minus the qth term of the sum is less than epsilon. Now, what we're going to do is we're going to take k to be h plus 1. So what we're going to do is, with this choice of k, we're going to show for all j greater than or equal to k, absolute value of xj minus 0 is less than epsilon. So let's give ourselves an arbitrary j greater than or equal to k. And from here, the whole goal is to show absolute value of xj minus 0 is less than epsilon. Now, since j is greater than or equal to k, we have j greater than or equal to h plus 1. Therefore, we have j and j minus 1, both greater than or equal to h. So what that means is, we can go to this statement and take p to be j, take q to be j minus 1. So then we have that this inequality is true, where p and q are replaced with j and j minus 1. And so that's going to be used to show absolute value of xj minus 0 is less than epsilon. Right, so if we write this out, we know that absolute value of xj minus 0 is just absolute value of xj. But then what we're going to do is we're going to add and subtract the j minus 1th term of this sequence. So then, focusing on the first two terms, we could append the xj to the sum, so it's really the sum from n equals 1 to j of xn. But we know from what we discussed before that this inequality is true where we take p and q to be j and j minus 1. So that means that this guy is less than epsilon. And so this shows that acid value of xj minus 0 is less than epsilon, which is exactly what we wanted. So we have proven this statement, which proves that the limit of the sequence of xn's converges to 0. And so we have proven if the infinite series converges, then the limit of the sequence of xn's converges to 0. And that's exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.